Yeah, so now we have Simonetta Liuti from University of Virginia. She's going to also bring us in this follow-up journey on nuclear physics. She's going to talk about what physical information is in deeply virtual exclusive experiments and how do we take. That's great. I'll leave you the floor. Thanks.
Okay. Well, thank you. Thank you for having me here. This is a great meeting. It's my second time here, and I am always enjoying it a lot. So, yes. So I would like to give you an overview of what this sector of QCD that we are studying is. And all of this physics will be soon, we'll soon be able to partially explored in various laboratories around the world, but it will be soon the focus of the electron-ion collider. This is why these issues are pressing now. So yes, so the electron-ion collider is a next-generation particle accelerator that will be built at Brookhaven, as many of us know. And what does the electron-ion collider promise? It promises, and this is on the webpage, and you can go see it directly. I took it from the webpage. Will be a particle accelerator that collides electrons, okay, to produce snapshots of those particles in terms of structure, like a CT scanner of the nucleus, for atoms. So what does that mean? Okay, so we know that how important imaging is. The whole day yesterday was dedicated to imaging, and then looking at the very large scales. We had, many, prominent examples of the importance of imaging. And one of them that was not mentioned yesterday, for instance, is the imaging of the black hole. How much we have learned going from the first image to the machine learning generated image of Sagittarius A star. Now, what we're going to do here, we're going to switch the gears and go all the way from the 10 to the 23 meters, away, so probing images at those distances, to the structure of the proton that is this whole world that exists for us at 10 to the minus 15 meters down. So we address these questions with this rather newly created XClaim collaboration, where XClaim stands for Exclusive Scattering Experiments with Artificial Intelligence and Machine Learning. Some of us are here in this picture. This was taken at the very beginning of the thing. In fact, Brandon's there too, which is not currently part of the collaboration. Yes, we like to collaborate, have many other, affiliates too. And these are the PIs, and we have several postdocs and graduate students. And the QR code is there for people to see. The UBA subgroup, in particular, includes Douglas Adams, Saraswati Pandey, Zaki, who's here, and Adil, who is stuck in Pakistan for months now, due to the current administration. So, and then there's Jitao at ODU, who's been doing a lot of the machine learning work. So, quantum chromodynamics, the theory of the strong interaction. So we know that this is SU3, the billion gauge theory, quarks and gluons. So what does that mean? It means that the gluons self-interact. This is the Lagrangian. The Lagrangian is pretty simple. You would think that, and many of my particle colleagues remind me, that they don't hesitate to remind me often, that, we know everything. We know everything, then there's nothing to discover. All right? However, that's where the potential for discovery is, and the interesting part is. So we know that QCD is very, very, it's okay, from this Lagrangian, we get these properties that are very non-trivial. We have asymptotic freedom and high energies. We know that the coupling constant decreases with the energy scale, so 1 over the distance. And so we know that the quark, anti-quark pairs of quark configurations are confined at low energies, and are strongly bound, I should say, at low energies, and move asymptotically free at high energies. We know that there's confinement, okay, although we do not know the real reason yet for confinement. We cannot explain it in fine details. And we know that it has, finally, third point, a rich vacuum structure. And where these quark and gluon fluctuations pop in and out of the vacuum. And the condensates are described in terms of instances and are color vortices, and that break chiral symmetry, confine color, and generate mass. So these are, in many respects, these are general highlights of what QCD is. However, when we get to calculate these quantities, we end up having a lot of problems exactly because of the non-perturbative nature of the theory. So predicting hadron properties, in our words, from first principles from the Lagrange requires solving QCD in the non-perturbative regime, understanding the non-perturbative-perturbative connection, understanding the factorization properties of the theory. However, even in a framework where factorization works, and so even in the easiest scenario, at a given value of the Haar scale, we know that we cannot predict the value of the factorization scale directly from the theory. So this is not a given of the theory. This is something that we have to live with pretty much on a case-by-case basis, okay? And once we extract the non-perturbative part, there are many largely unknown layers that separate the observable from the dynamical and topological properties that we want to understand. Suppose that we have a theory, instanton-based theory, any theory, your favorite theory. How does that reflect onto the observables in a way that it cannot be considered ad hoc? I can explain the observables with a bag model or something, but way simpler than the fundamental theory. So lattice QCD is there, luckily. And however, it provides only partial answers to the questions, because sometimes the answers are given in the form of a black box that is not interpretable. And this is what this talk is going to be about. So let's start from defining a little bit better factorization in a nutshell. So this is a Haar scattering process, like one of the processes that you would see at the IAIFI. The electron scatters off the proton, for which we can write a Feynman diagram just in view of factorization. That means that we can write this process, we can separate out the Parton distribution function in this blue blob, which is the non-perturbative blob, from the Haar process, which is here, when the electron scatters off a semi-free quark or gluon. And then finally, there is the fragmentation process. And in this case, it's represented by a metal, but there are many more possibilities. So we want to understand, why, the whys of the theory, essentially. Why is there this scale? Why is this ubiquitous scale of lambda QCD that appears everywhere in the theory? And so for this, we need explainable AI methods. And one of the methods that we have been exploring is this, is using this, basically a post-hoc analysis of a form of the variational autoencoder inverse mapper lattice space. And that connects a little bit to the talk before, although I'm just going to show you just a little bit of that part, because I want to focus mostly on the interpretable AI methods. And in a 30-minute talk, I have to make choices, but we are here, Zaki is here, we can definitely answer questions on this, and we hope also to be keeping the conversation going. So to understand the why, you have to go to explainable or interpretable models, as opposed to the standard machine learning models that are more geared towards understanding the what of the theory. So okay, and so there's a potential of directly enabling discovery of laws in nuclear particle physics that connects with the talk before. And it's not just a set of advanced computational tools, it's about finding a common language between physicists and computer scientists. That is very fundamental. That is why this extreme collaboration is sort of like working, because we have our computer science experts, and then we have phenomenologists and lattice QCD theorists all together, and one experimentalist too. Okay, so interpretability and prediction. So the goal of physics is to extract information as accurately as possible from data. This is a little bit repeating what was on the slide before with a little bit more detail. And so we want to have concise, understandable equations that are understandable. And while machine learning, it's mostly like only predictivity. So the goal of the standard machine learning is predictivity. And so it's to obtain statistical models that make predictions from the data. And so very, very, very often we're lacking that interpretability issue. And so all of this, okay, in our problems, and I'm going to show that to you in a moment, is encapsulated, embedded, is captured, I should say, by this inverse problem that we, by the set of nested inverse problems that we find in QCD. And this is why we need that have to be addressed, in my opinion, only with this close collaboration of computer scientists and theorists, essentially. So what's an inverse problem? What is an inverse problem? What is not an inverse problem in general? What is the inverse problem that we are faced with in QCD? So we have our theory. This is where our Lagrangian sits. Our theory of color quarks and gluons. And suppose that we have factorization theories that we can form observables. And so this is the phenomenology part. This is where we come in. And then we test these observables with the experiments, for instance, the electron-ion collider. However, so this will be, if we go from theory to experiments in a forward way, this will all be simple because we will go from, the many variables to predicting one variable, and that will be easy. What we are faced with is that we have the one variable that comes from experiment, and that we have to go all the way back and understand where the many, many aspects of the theory where this came from. And that's what I mean by inverse problem. This is so that we're all on the same page. So what is our physics case? Extracting information from deeply virtual exclusive scattering experiments. So what are these experiments? So in a QCD factorized scenario, so we're going to assume that now QCD is factorized, quark and gluon, we want to obtain quark and gluon spatial configurations from this deeply virtual exclusive scattering. So what does that mean? This is this type of experiment that we're looking at. So we have an electron that scatters off the proton, and now the final state, differently from your deep and elastic scattering experiments or differently from your elastic scattering experiments where you look at form factors, we select one particular final state that happens to be very important for our predictions. That is the state in which the proton scatters off and emits a very high energy other particle that in this case is a photon. And when it is a photon, we call it deeply virtual Compton scattering. But it could be a meson. It could be any other particle that comes out at this hard part of the cross section, as I shared before. So this is why it is an exclusive experiment, because we are measuring only those two quantities: the high energy photon and the proton scattering off, in addition to the electron. So now this seems like. So this is what the experiment is. It's complicated, and I'll show you the cross section in a moment from the formal point of view, because just writing the cross section, because instead of being able to reduce it to a 2 into 2 process like we always do, like it's in your particle physics book, in your Hudson and Martin, okay, we go always in this case from 2 into 3. You can't escape that, and that in itself produces a whole lot of complications, more than what you would think. But they're interesting. let me say that. So, okay, this is how we describe the amplitude. We have for the process, we know how to do that. There are illicit amplitudes. We have a lot of expertise. The soft part, so where the physics, the interesting physics resides, is this generalized Parton distribution. So now this generalized Parton distribution is going to be both sensitive to the longitudinal dependence of the quarks, like in deep elastic scattering. But now, because the protons, initial and final protons, have different momenta, it's also going to be sensitive to the momentum exchange between these two protons that is different, in this case, from the scale of the interaction. So in deep and elastic scattering, the proton scatters off, and there's no such a variable as an exchange between the initial and final proton. We don't know where the final proton ends up, if there is a final proton in all the possible final states. Here we have this extra variable, and this extra variable is important because by Fourier transformation it allows us to access the spatial dependence of the quarks inside the proton. So this is why these reactions are interesting or promising new insights. So GPDs, okay, encode information on that, I said that. And the other aspect that is interesting about GPDs is that if you calculate the x moments of these GPDs, so now we integrate over longitudinal momentum, so many moments, they encode information, the moments of order 2 encode information on angular momentum, on the angular momentum that is carried by the quarks and gluons. And so they allow us, in other words, to access this orbital component that is seen as by many, and again, I am agnostic about this some rule, as the missing part of the proton spin puzzle. So that's why there's a lot of promise in these observables. That's why a lot of the program at the EIC is going to be about measuring these observables. So that's the cross section. Yeah, I haven't seen many formulae in this meeting so far. This is it seems it's ugly, but it can be divided into observables, and I have to show it to you because if I don't show you this, it is very hard for me to communicate the concept of inverse problem. So in other words, this is what we go out and measure. Say that we have an unpolarized target. It's going to be just focused on this orange piece here, and then we have 1, 2, the F are the functions, the structure functions, 1, 2, 3, 4, 5 structure functions, and 1 observable. This creates, obviously, a first inverse problem. Okay, so that's what goes on in the cross section, and then there is more because these structure functions now we want to divide them into. We want to get to the GPDs, so we have to go from these structure functions to their internal components that are these Compton 4 factors. These Compton 4 factors are characterized by their QCD structure, twist 3 and twist 2. It doesn't really matter to us now, in the sense that there is no how. Just a remark that the twist 3 components are very interesting because they actually really are tied to these orbital angular momentum, spin orbit, and transverse spin and transverse orbital angular momentum components. So there's interest in that. And so. And then again, so we go, as I said, there are many layers between the Lagrange going down, and the observables, okay? And this is one case. And this is the problem that I chose. Any other problem in QCD that look at CDs, semi-inclusive deep elastic scatter, look at any other problem is going to be similar. This is the problem that I'm interested in. So the Compton 4 factors in turn are written as integrals with the perturbatively calculable QCD kernel of these GPDs. So you have to extract, in other words, the GPDs from an integral. And that constitutes a second inverse problem that is even harder than the first one. Because now, you have the quantity not in a summation, and now you have not in a discrete sum, now you have it inside an integral. So there are these two nested inverse problems, in a sense. Okay. Once you get that, you're not done in order to get to the radius. I showed you the EIC result. I said, what is the EIC promising? That is the CT scanner. That's what you have to do. These are the steps that you have to do to get to the image. So once you do that, you have to do the Fourier transform. And that is non-trivial. And this is like a simulation that our colleague, in one of the many lattice calculations. So this is our approach to the problem, the exclaim approach to the problem. So we started from looking at the statistics really well. Oh my gosh, the time is running. And developing machine learning and AI algorithms. And then, moving our way up to understanding, how to extract these Compton 4 factors and possibly addressing more theoretical questions. So does factorization work? That is the question that is in the back of my mind from the very beginning of this collaboration, and that we are in the process of addressing. Okay, so most of this work that I'm going to show you is now moving from the dot below on the statistics, and this is where it becomes interesting. So, all right, these are the data. These are from an experiment at Jefferson Lab. And the data are plotted as a function of this angular variable phi. The angular variable phi is the other angular variable that you need, and therefore, because of the 2 into 3 process, because you always have an azimuthal angle, because you're always going to have a third particle that's going to come out off the plane. And so, so what we noticed is that, we took the data, we just tried to do curve fits. So basically, these using our Compton 4 factors as parameters. And this is a highly degenerate problem. So we can choose one of the Compton 4 factors, this real part of E, like in a wide range of values, and still we get the same chi-square for the curve fit. And the values up there are really teeny tiny, yes, but trust me, they're the same chi-square. So, okay, so that means that the extracted Compton 4 factors are significantly sensitive to the way the fit is done. And so we just did a standard likelihood analysis, with an uninformative prior. So we took priors equal to 1, evidence equal to 1, and Gaussians everywhere. And we evaluated the likelihood with an MCMC Metropolis Hastings algorithm. And what are our results? Well, first of all, from our formalism, 3 of these Compton 4 factors are extractable from the theory, and these are called E, H tilde. This is the they mean something, but let's focus on the names here. And so what we found is that yes, we can extract them. However, by exploring all of the possible phase space and likelihood analysis can do differently from the curve fit. However, these values are highly correlated. And so we found these correlations that were never found before in the data. And we tried another method. Bang, the correlations are still there. And we looked at the marginals. And the marginals, our orange points are here in this plot, show that basically there's a huge spread of the results compared to what was found in curve fit results that appear now and then in papers from some experimental analysis. So the statistics has to be taken seriously, and this is the first part of our that I would like to convey, and that's an important part for us, and because you can learn things. For instance, you can, there are approximated forms of the cross-section that have been used over and over by experimentalists that are called BKM and Brown et al. Forms, which are not going to be working because, and they give us these degenerate results, these black curves here, and that we can rule it out with our likelihood method. So this allows us also to understand what parts of the cross-section are important. And with that monstrous cross-section that I showed you before, I mean, again, let's keep our eyes on the prize here. That's the radius. We're not going to do that if we don't start from step 1 in a very thorough way. All right, and we understand why those those degeneracies appear. We can look at them, and more on this if anyone has a question. We can also suggest new observables. So we, from our analysis, we can tell, okay, let's not go and explore the whole phase space and look at many kinematic values and many bindings, but let's just choose another type of observable that can help us with the degeneracy, help us reducing the degeneracy at the same kinematic point. And that's, again, another important information that we as phenomenologists are providing to experimentalists thanks to this likelihood analysis. We can look at other quantities, and this is where factorization is going to come in an interesting way. This is done mostly by Saraswati Bandi here. We can look at pi0 electroproduction, and now there's a pseudoscalar, and there's many more interesting properties of that. And we can study factorization because now with this type of data, we can now look at the helicity amplitudes disjoint from the Compton 4 factor, so even before factorization happens, and study whether factorization is going to happen or not. Okay, so the first, this is the step, like getting the statistics right. And now, second step is developing the machine learning and artificial intelligence algorithms, which is the main part of my talk. But it'll be fast enough. So, one, I don't want exactly. This is fast. Variation autoencoder, conditional variation autoencoder, and MCMCs and their connection, and so on and so forth. I will have to skip fast on this. I mean, go fast on this. This is what we know. So we can also now, basically have a set of priors, and not be agnostic. And now there's not going to be just 3 of the combinatorial factors. All 8 of them, there are 8 in total, can be derived. And the interesting part of this is the analysis of the latent space, which is, again, in tune with the previous speaker, which did a much more accurate job. We're just now, basically, we know that we have this latent space. We know that there are certain combinatorial factors where the latent space is not structured. That's all we could do, is latent space not structured, latent space structured. That's all we could do. This combinatorial factorization as a latent space structure means that the variation autoencoder captured everything. Here we see that there's a sign in this other combinatorial factor. So this combinatorial factor there's going to be a sign. It's going to be with a plus or a minus in their interpretation, which we see here when we plot them here. And then this is the most interesting one, because we see that there is, a circular form, and that means that there's periodicity or oscillations of the combinatorial factors. But we are only at this step in which we've been just basically staring at the latent space, and we are here in the process of doing a more systematic analysis. This is the core part, symbolic regression. So what are the existing tools here? These are the various existing tools. I'm going to show results using PySR. And again, I'm using PySR. I know I'm here in the hub of other tools. But we're using PySR because it's the simplest to apply. It's the one that's it's the simplest, but we are open to using more. And so in a nutshell, what does it do? We have a data table. There are 2 criteria: goodness of fit and goodness of form. Both of them have to be satisfied simultaneously. And we train the net based on a loss built on these 2 criteria. And the question here is, why bother with SR when we have the neural networks? Well, okay, it's all about interpretability. And here we applied it to lattice QCD data, let's call them. So this is how the lattice QCD data look like. Lattice QCD can calculate. Remember that X and T dependence of the GPDs. We can calculate it in lattice QCD. And this is what they give us, which is fine, but what does it mean? Okay? So can symbolic regression help us find an interpretation of this lattice data? And in particular, for instance, we have X and T dependence. Does this X and T dependence factorize? Like I have it as a problem of f of x and a g of t. Does that happen? That's important because if we think about the coordinate space dependence, the Fourier transform, if the x and t dependence is factorized, then I will have a radius of the nucleon when I do the Fourier transform that is constant. There is a constant over the whole range in x. So every partonic configuration with a given x value is going to have the same radius. Does that make sense from the point of view of QCD or not? So we can start asking questions. We can start trying to understand the theory. Okay? So this is how we managed how we found our best fit functions. And we have developed, this is a new thing, a PySR convergence criterion. And this PySR convergence criterion is based on a Taylor expansion around one of the points in the lattice data range. And so we go up to coefficients up to A equal the 5th coefficient in the Taylor expansion and see how well these functions agree. And why do we need a convergence criterion? We need a convergence criterion because we can have many expressions, analytic expressions in PySR that simultaneously fit the lattice results with the same value of just equally fit, that are completely equivalent. Which one do we choose, and why is it so? Okay, so this is why we need a convergence criteria, in the sense that we're now going to go from the lattice region where we have this overlapping functional forms to the region where we extrapolate. And when we extrapolate, typically you get a whole range of values. And the convergence criteria allows us to essentially single out through this the values of the coefficient of the Taylor coefficients 3 separate clusters, and allows us to interpret how the lattice data extrapolate in the unknown region. And these are some examples of our best fit and force factorized fit functions. These functions are very interesting. We're now looking at these shapes one by one and trying to understand what they mean, like whether they have a probabilistic interpretation or not, for instance. And there are some very interesting forms. And what we found is that the data mostly seem to factorize. So these are the lattice ratios of lattice moments in red. Here, there's when the ratios don't go flat, as I said before, there's a hint of non-factorization. Here it seems that the lattice results for one of the moments factorized. Here, there's more uncertainty, let's say. The green points are our predictions, which always factorize, and even when we violate factorization, they're close to factorization. That's why they appear as these green points all in a line. So this is a result that we're getting from scratch out of our theory. So we can, Fourier transform and get the densities out of those analytic forms. And here are our radii prediction. This is the radius of each partonic configuration. So this is partonic in this sense. We are not looking at gluons so far. We're looking at the quark inside. And you see that this is as a function of x. There are some configurations where the radius blows up, and so those will be discarded, and some configurations where the radius decreases, and this is where the factorization, the approximate factorization holds. So we can study all of these configurations now. So final point. So this was for symbolic regression. The next point is we can also do a neural network GPD and an end-to-end problem. So you know that the GPDs enter both the moments by now and the Compton 4 factors. So in order to go from moments to Compton 4 factors, we always go down one level and then go up, or from this direction where the lattice QCD data exists, to this direction where the experimental data exists. What about the end-to-end problem is, what about if we could connect the moments and the Compton 4 factors directly and see, because they're both given by GPDs, so that they should have that information. It's just a matter of what information is in there, if that information is in there in the experimental data. So in particular, this is going to be, as I said, sensitive to angular momentum. So is the information on angular momentum directly extractable from the data? That's what's bugging me, because I would like to know if that is in the data. So to do this, I show you these preliminary results of a diffusion model. This is how our loss function looks like in the diffusion model, which is standard. It's a little bit different. I don't know if the person that was giving the talk yesterday is here, probably not. He had a different way of looking at the loss function, and I would like to connect with him, but maybe I'll find it. So this is our loss function is standard, and so for the sake, so we are finding that indeed the predicted and the true values are lining up, and so the diffusion model seems to be working like a charm so far. I need to understand this a little bit better, but this result is so astonishing that I decided to present it anyway, even if I am just personally starting to look at it. And that's all. I mean, forget about that. Last but not least, AI for EIC meeting in here in October. I'm advertising for that. Cristiano Fanelli is one of the organizers, is here. Brandon, the convener, is here. And so this is, I think, another venue where we will be able to get together. And so let me just leave the conclusions up for reading, because I'm sure I'm super late. No, not super late. Okay, I managed to accelerate in the end. And yes, that's all. Thank you.
All right. Thanks, Simonetta, for the talk. And we open the floor for questions. I see one. Let's go. Okay, just stay on this side.
Thank you. I wanted to ask you to elaborate more on this convergence of the PySR solutions. How?
Yes. Yeah. So actually, it should. It's so maybe convergence is a tad of a misnomer. So this is the situation. So we train our network in networks in general in the lattice. So the data that we have to train anything is in the lattice region, which is this one here in gray. And so when we get the analytic forms from symbolic regression, we get a spread of forms here. I mean, the forms, they are good where we have the data, and then obviously when the data are missing, they just go from minus infinity to plus infinity, roughly speaking. So, however, we have this bunch of solutions, and so with this convergence criteria, so what we did is we took a point here in the middle, and Taylor expanded around this point, and looked at the Taylor coefficients, which are here, up to the fifth coefficient. And we took the ones, and we took the ones that, and this allowed us, in other words, to separate out the solutions where in the extrapolated region in three different clusters, out of the behavior of the Taylor coefficients. So they cluster in three. There are three different clusters of solutions, and these three different clusters of solutions are in color here, okay. This doesn't have any physics content in it. It's just a mathematical procedure, and it's what we could do so far. However, it is a step forward as opposed to saying we know nothing where the data don't exist. SR allows us to, because of the functional form, allows us to single out what type of solutions we have in the unknown region. And then yes, and so that's pretty much the case. What would be good to do to improve on this is to now ask some more questions, like physics questions, like okay, the solutions that we find, are they compatible with a probability distribution? This is supposed to be a probability distribution. Are they compatible with the probability distribution or not? So put in more physically stringent criteria. This is just a mathematical criteria. And it's quote-unquote convergent. I don't know if it answers.
Yeah, perfect, thank you.
Okay.
Yeah, just on this slide, actually, just out of curiosity, what are physics constraints you expect to have in this extrapolation regime to constrain this? Because you can...
Yes. So they were not applied here. So the physics, so they're applied in other instances. When we look at loss functions in other instances, we do apply those physics constraints. So there are a bunch of physics constraints that come from the symmetries of the theory. Like, for instance, this is... I don't know, it's a U-valence minus D-valence. It's a non-singlet part. I'll give you an example. And so when you plot it as a function of x, it has some reflection symmetry properties. And then again, there is baryon number. So you can impose that this is, these are the U-valence. When you integrate this over x, you want this to be 2 for the U-valence and 1 for the D-valence. So there's baryon number. So that's another physics constraint. And then, Zaki, remind me of the physics constraints. The Mellin moments, that's the baryon number, yes. Yeah. And then, sorry? Yes, yes, yes. So there's variations on the theme of that. And the positivity also. The positivity. There's a positivity constraint. So this is a generalized partial distribution, has to be lower than the form factor. Okay.
Just to get an impression on numbers, is there an infinite number of constraints you can impose, or is it a finite number?
We have them listed in one of our papers, in the variational autoencoder paper. Yeah. In this paper, they're listed in the VAIM paper, and here, and they're like it's a finite number, 4 or 5 constraints. They go all into the loss of this, so it's all they're tractable constraints. Yes.
Any other questions? Or more?
So I'm very interested in how you assign the uncertainties on the extrapolated region, right? Because you have a family of solutions, but how do you differentiate which one of the solutions like contribute more or less to like different systematic uncertainties just because of the fit?
So systematic uncertainty. So in what? In the symbolic regression problem?
Yeah, in the extrapolation region.
That's a very good question. We are not taking into account the systematic uncertainties from the lattice. We are not. So this is all based on statistics. So yeah, that is a very good, because, well, Will is here, can answer in a much more appropriate way, because the lattice data are not simple. I mean, they have correlations, they have covariance matrices, and so on and so forth. So that is a whole. So to put in there the systematic uncertainty is a whole new ball game that we like to play, but it's not here.
And on these 3 different clusters you obtain from the PySR convergence criterion, how do you determine like which one of them like contribute more or less to the solution?
And that's the beauty of QCD. Of these Proton distribution functions, they are the unknowns of the theory. I tried to explain at the beginning. That's the non-perturbative part of the theory that we have no way of evaluating from that Lagrangian, from first principles, even if we know the Lagrangian really well. I mean, it's just not complicated. We don't know how to predict those, and so that's why lattice QCD helps. But then what lattice QCD tells us is here. This is the behavior. Then if we want to interpret them and put some dynamics in some dynamical interpretation into that, then that's what we're trying to do. And so, for instance, so let me just give you this example. That's why I showed the radii, like the different solutions. You see the green, the yellow, and the red. They correspond to those clusters. So if you take the distributions from the yellow clusters, they're not good. They're not good if you go and look at some other observable. Because they predict a radius that blows up for some value for some partonic configuration. And we haven't seen that happening in the experiments so far. And while these, the green and the red, are okay. So then there are other physics criteria that one can build on that. But there's no unique way of looking into that because.
Thanks.
Right. If there are no other questions, we can thank one more Simonetta for a wonderful talk and just transition to the break. And we'll